The 2021 Wisconsin Science Festival. Hybrid, hands-on, and virtual. Events throughout Wisconsin for all ages. Discover the wonders of science and the power of knowledge with a focus on fungi with scientists, live Q&A sessions, science experiments, and more. Plus, PBS Wisconsin Education launches 2 new interactive labs in the Meet the Lab collection. Full schedule at wisconsinsciencefest.org. Curiosity unleashed.
Awesome, fantastic. Welcome everybody to the Wisconsin Science Festival. Whoa, look at that. I was surprised by that. That's a little spooky. You see a little preview from our scientist, Liz. We're here today and we're gonna have some fun. And I'm Travis from the Wisconsin Science Festival team. And as you can see from that steaming pumpkin, Liz, our scientist, is gonna join us for a field trip online today. And we want you to participate. So you can participate a few ways. If you have comments or questions or want to spark some conversations, you can use a chat, but certainly we want you to use a Q&A feature whenever you have a question that sparks from the investigation that Liz is going to guide us through. We want your questions because that's going to guide what's next in science, as it always does. The field trip's going to be recorded, and we ask that you do this in all activities with a responsible adult. We'd like to thank all of our sponsors as well and partners that make the festival happen, including Liz's connection to BioTrek and UW-Madison. Super amazing. You can find out more about this event going on today with field trips and follow-ups and other things happening around the state at wisconsinsciencefestival.org. So with that, we are so excited for our field trip with scientist Liz, and hand it over to you, Liz. Get us started.
Excellent. So this is already a really good question. What's coming out of my pumpkin? Very good question. All right. So this is a lovely pumpkin that I carved last night, and in it is a cup of hot water. All right. And what I'm dropping in it is something that is incredibly cold. So this is dry ice. And dry ice is the solid form of carbon dioxide. It's incredibly cold. You don't want to touch it. So this is why I have a very thick hot mitt right now. You think, why would I want a hot mitt if it's really cold? Same kind of protection. And then when I put it in the hot water, you can see that it very quickly, all right, lets off a lot of awesome water vapor. All right, so this isn't anything too scary that's coming out of it. I can touch it, and it's nothing that scary. It just leads to like kind of a cool example of how science is pretty amazing and fun and all sorts of great stuff. And that's why we're doing some fun stuff today. So that kind of leads me, I guess, into a little bit of who am I? What am I? Why am I here doing this? I have I have an interesting science background, as I think a lot of scientists do. I didn't originally know that I was going to be putting dry ice in pumpkins for a living, right? When I grew up in Madison, actually, and I really wanted to be a veterinarian for my entire life. And I was set that that's what I was going to be. I wanted to be a vet. That was it. I loved large animals, small animals, you name it. And then when I was in high school, I really fell in love with bacteria in an advanced biology class that I was in. And I thought, okay, maybe I can do a combination of one thing or another thing. And then I went to UW-Madison, still wanting to be a vet, and bacteriology, surprise, surprise, is a major that I could major in. And I was like, oh, I love bacteria, and it's going to possibly get me into vet school. So this is even better. But when I applied for vet school, it's really difficult to get into vet school. And I was put on a waiting list, and I said, nah, I'm not going to do that. I'm going to continue on into my science career, and I'm going to go on a different branch. All right. So I moved out to DC, and I actually worked at a biotech company called MedImmune. And if anybody people are getting the flu vaccine right now, right? In addition to the COVID vaccine, my company was working on one that if you had issues with shots and couldn't take shots, or if you were elderly or very young, we were developing a flu vaccine that went up your nose. It's called Flu Mist. So I worked on that for a while. I was a purification technician, big fancy name for running these big long columns that we would run the drug through to purify it. But when I was there, I realized that sitting in a room, all right, kind of by myself, not with a lot of people for 12 hours at a time, wasn't exactly the kind of science that I wanted to do with my life. And I also looked around my surroundings, and I said, there's not a lot of women that I work with. And I said, what is happening? What can I do to help get more women into science? So that led me to, why not be a science teacher so that I can spark interest in science from the very young, and hopefully that'll continue on to older years. So I went back and I got my master's degree in secondary education, and I taught for 10 years, kind of in the Sheboygan area at public schools. I taught at middle schools, I taught at high schools. And then I'm a mover and a shaker. I don't like sitting in one place for very long. So I kind of moved my path again. And I said, well, I don't want to be in the classroom, but I still want to be teaching somehow. So when I moved back to Madison, I found out about this cool career called science outreach, where you can outreach to various students, and you can run experiments, and you can help design experiments with them. You can run workshops. So that's what led me to the Biotechnology Center, where I work at BioTrek, which is the outreach kind of leg of the Biotechnology Center, which is where I am right now. And if I was outside this is our prep room. So it looks very sciencey, doesn't it? There's electronic balances over here, right here. This is my ice, but over here is a thermocycler that you use for PCR. So that's a really fancy tool as well. So I get to use all these fancy tools. Oh, I'm getting this out of the way. Good, so I don't touch it. Cool. So we're gonna do a little something today. All right. Any questions before I get started? I'm gonna move my friend over here if you're okay with that. Cool.
Yeah. Oh my gosh, we might have to bring your pumpkin friend back. I know that it's kind of fun to think about some of the things you do at BioTrek, because pumpkins might even have parts that other living organisms might have too. And maybe we'll learn about that today. Yeah,
so you can extract DNA from pumpkins, which we have done before at BioTrek. So yeah, actually I was playing around with that last week because we had a 4-H spooky science event last night. And we were gonna extract DNA from pumpkins, but it takes a little bit longer. We normally do it from wheat germs. So we decided we don't have that much time. So, but you can extract DNA from pumpkins. So good connection, fantastic. All right. So
let's get started. Yeah, what kind of tools are you going to start off with here? Because I know like Preston had a couple of excited notes in here, and some other students might be excited too to see what those tools do.
Oh, what these tools do?
Yeah.
Oh, cool. Okay. Yeah, I can show that. All right. So these, actually, I'll show you something. This is kind of cool. This is an electronic balance. So it's like a really fancy, expensive balances where you can measure really, really small amounts of things, find the mass of very, very small amounts of things. So we're talking about quantitative measurements here. So I want to know exactly how many grams or 0.5 grams or whatever I'm looking at. I can just put it on this scale, and let's see, I can even turn it on. Oh, I turn it on. All right. And usually you'd use a little something called a weigh boat fun tools we use in science, because I wouldn't want to put something directly on this balance, right? And then put something else directly on this balance, because contamination is a pretty bad thing in all branches of science. So instead you put that down and then you zero it out to make sure that it's zeroed and starting from scratch. And then I can put a little something in there. So I don't know, let's see, I could put, I don't know, I'll put another wayboat in it. I have tiny little, oh, these are adorable. I have tiny little wayboats too. So I'm gonna put a tiny little wayboat in my bigger wayboat. Let's see. It has a mass of 1.094 grams. So it's also very precise, because we can go many points past the decimal point as well to get a very exact, precise number with these balances. So that's an electronic balance. We got a couple of those. And then we also have, these are really fun. This is a stir plate, and it also is a hot plate. So I can put something on here and I can, oh, you know what? Maybe I can do it. Maybe I can do it. I think I can. All right, so I have this little container. And this is magnetic, all right, which is really cool because check this out. All right, I can go over here. I have all these bars that are also magnets. So
cool.
I can put this in my bottle, put my stir bar, it's called a stir bar, put a little closer in there so you can see it, into my other jar. And then it, when I put it on, it immediately sucks it down so that it gets really close to that spinning. So the magnet, there's another magnet here that's going to spin. So if I turn this on, you maybe can't hear it. Maybe you can. All right. Ooh, we start slower. Oh, oh, oh. Oh, this is, I think my bottom is a little rounded, so it's not spinning very well. I apologize. But it should be spinning, but my container isn't quite the right size for the right bottom shape for it. But I also can heat things up on here, because what's cool about chemistry and a lot of other cool sciences is that sometimes you have to heat a solution up in order to get more stuff in it. So think of it if you're making, I don't know, if you're making like caramel or something like on the stove top. You ever watched a parent or a guardian or older brother or sister make something like that? And you put a whole bunch of sugar in it and you can stir it like crazy when it's cold and it's not going to dissolve all the way. But if you give it a little heat, then you're going to allow that sugar to dissolve. So that's why we have a stir plate that also is a heater. So in case if the stirring doesn't mix it up, then we can just add a little heat and then we can get it to mix and dissolve. So
that's super cool.
That I get.
That's really awesome. Yeah, yeah. All right.
Okay. All right. Are we ready for the big activity for the morning? Ooh, hello. All right. So does everybody have hopefully the materials that they need? You're gonna need, I think we asked you to have some cups and some straws and 2 types of milk, right? Because the big question for the day, and it's an interesting question, so we'll talk about it a little bit as well, is which makes better bubbles, skim milk or whole? So if somebody would ask you that question, and you can go ahead and throw your response in the chat if you want, and I can read them, or Travis can tell me some answers. How would you respond to somebody if they said, which makes better bubbles, skim milk or whole? And then maybe give me an explanation for why you would answer that way. So how would you answer it, and why would you answer it like that? Oh, somebody just said skim milk. Yeah, okay.
Yeah, and maybe some clues. I like that idea of like, why would you answer? I like that idea. Why do you think slim? Like, just what pops in your mind? Any words that like, that's the one for me. Like,
oh, somebody said they're both milk, so you think the same. Good reasoning, right? So I see we're kind of using our knowledge or our background knowledge of what we know about milks to come up with possible responses, right? So I got to tell you, I'm kind of a trickster because the question that I gave you is pretty ambiguous, right? So that's kind of a big word, but maybe you can think about it when we go through this experiment, okay? Because a lot of people have different answers, all right? But as scientists, we don't just say, oh, well, I think this, and that is why. Instead, we test it, right? So we're going to ask the milk. The milks are going to tell us that answer, okay? So we need some materials, right? And maybe we can work together and figure out what we exactly need. if we are testing 2 types of milk, how many cups do we need? We're trying to create a fair experiment here. All right, so think about making it fair. That's the big thing it is. How do you make an experiment fair? All right, how do you make a test fair? 2, I see 2, I see a whole lot of 2s. 2 or 4. We're doing multiples of 2. I like that as well. Okay, 2 half cups. Oh, and good, we're talking about amounts because we're going to get to that as well. Okay, so I see the majority of our young scientists are saying 2 cups. So I have 2 cups. You guys probably have 2 cups as well. Pretty good. Before we put any milk in here, though, we have to think about how we're going to tell the difference between the milks, because I don't know about you, these milks look pretty much the same to me, right? They look pretty much the same here, and they look pretty much the same when we're going to pour them in the cups, right? So we have to either, right, label our cups, right, to know the difference. So I'm labeling my cup because I have plastic cups. If you have cups that are, you don't want to mark with a Sharpie, totally get it. Then you may want to put a piece of paper underneath your cups, or put little pieces, tiny pieces of paper, and rip them up, all right, so that you know which is which. So that would be good as well. The big idea is just to make sure that we know which is skim and which is whole. Okay. All right, so now we got our 2 cups, rock and roll. Now we have to figure out how much are we going to put in these cups? How much do we want to put? We already got one answer from Zoe and Chloe. Chloe, good name. That we're going to do half of a cup. Half. Any other responses? What do you think? Well, I'm here. I'll throw another question at you. Does it matter? Does it matter if it's 1/8 of a cup, 1/4 of a cup, 1/2 of a cup, a full cup? Well, a quarter, got a quarter as well. Nice. So does it matter how much we put in it? A quarter. What do you think? Tough questions today. Oh, so it matters. Okay. Should they be the same, or should they be different amounts in each cup? What if I throw that little question at you? Should it be the same amounts or different in my 2 cups?
I really like the way that the scientists are having a conversation and talking about how to do an experiment. This conversation that's happening in the chat is kind of similar to the things that I've been able to be lucky enough to be a part of in talking with scientists and planning an experiment. How's it going for you, Liz, to plan this experiment?
Yeah, I think what we're kind of talking about here are things that are variables, right? So things that may be different. And when you're designing an experiment, you want things to be the same as much as possible, right? We're only wanting to change one thing at a time. Because if we change more than one thing at a time, how do we know what's creating that difference in the 2 things, right? So the same, I like that response, very good. So it really doesn't matter if you have a quarter or a half or a full, 3/4. Well, it may spill all over the place. Hey, that's you do you. If you want to have milk volcanoes, that's totally on you. All right. But I would recommend 1/4 to 1/3 of a cup. All right. And have that be identical. So go ahead and fill your cups up now to whatever your amount is going to be. I'm going to do 1/3 of a cup because that just seems to, I don't know. I've been doing this for about a year, and 1/3 feels pretty good to me. And it seems to get a decent amount of bubbles. So I'm going to do about 1/3 of a cup, just so things don't get crazy. And keep in mind that your milk is very cold right now, okay? So we're maybe going to be dealing with a variable that we maybe can't really change. Unless you have your milk in ice right now, then you're controlling that, right? But our milk is probably going to warm up a little bit as we do this. So that's going to be an interesting variable that we can't really control, right? Okay, so I have 1/3 of a cup. And then I'm going to get down real low here, all right, so that I can make sure that I have about the same in my skim cup. All right, ooh, that's looking pretty good. So it doesn't have to be like identical, but it should be pretty close. Ooh, all right. Travis has got some, oh, he's even got fancy straws. Oh my goodness. All right, so I have about 1/3 of a cup. Travis, what did you go with?
It took me a moment, but I went with 3/4 of a cup.
Oh, you are a daring fella. All right.
And I did that because that was my measuring device that I had that was handy.
Okay. For your for your most precise measurement and accurate. Very good.
Mm-hmm.
So good. So anybody else want to say, what do people use? Do people go with a half or a quarter? It's kind of nice to know what we're dealing with in the group here. I bet the group that was talking about a half probably went with a half. But either way, as I said, you are designing this experiment. All right. Oh, somebody went with a quarter. That's pretty good too. And that's what's great about science as well, is that if you're running the experiment and you're designing it, you are doing it yourself, right? So you get to make those judgment calls. All right. I'm not going to tell you, I'm not going to give you a big long list of instructions for how to do this. You're designing the experiment, this fair experiment on your own. All right. So the next thing is we need to figure out how many straws we need. If we have 2 cups, how many straws do we need? What do you think? This might be a few too many, maybe. All right, 2, cool. So I have different colored straws here. I don't know about you. Looks like Travis has just metal straws, same color. They're pretty much identical, right? Travis, I bet. Cool. All right. Somebody found a little emoji for a straw. That's adorable. All right. So what I have here is I have 2 different colored straws. I have a blue one and I have a red striped one. Okay. If I want to make it the most fair, I would put that red one back and have 2 blue straws. Does it matter? Maybe not. So I could test it both ways, or I could just get rid of that difference and make sure that they're both blue. So that's what I chose to do. All right. So I have 2 blue straws. So far, everything is the same in our experiment, right? The only difference is going to be we have skim milk and we have whole milk, right? And then we'll talk about any other differences that might be in that milk in a second as well. All right. So we have our 2 straws. Oh, now there's even another variable. How are we going to blow our bubbles? Are you going to blow them both together at the same time? Are you going to blow them one at a time and then another? Think about how to make it the most fair. How will you take out the most, any differences? Somebody said at the same time. All right, both straws at the same time together. Okay. All right. So you could try it both ways, or I'm going to do it together because in my opinion, as a scientist designing this experiment, I as well, all right, think that I'm going to do them together. Because do I know for sure if I blow into one, is it going to be the same amount of force as if I'm blowing into the other straw? Okay, so that's my reasoning for why I'm going to do them together. All right, are you ready? Let's get started. Enough of this talk. Let's get to blowing some bubbles. All right, so go ahead, whatever way you're going to do it, with at the same time, or however you're going to do it. Let's get blowing. Let's take a look at some of these bubbles. 1, 2, 3, go. All right, what are some differences that you're seeing right off the bat? What are you seeing? What are some characteristics of the bubbles that you're seeing? Travis has some milk that's not bubbling very well. What are you seeing? I'm seeing that there's some different sizes in my bubbles for sure. For sure. And go ahead, feel free to do this again, right? Do scientists just run one trial? Never. That's not a good experiment, right? So get in there, and if your bubbles go down, then go ahead and blow some more. All right. All right. So far I have size, and then, okay. Very big. So somebody said they don't see any small ones. Interesting, because my skim milk has some pretty tiny bubbles in it. So we've got size so far. Very good. What else? I see a lot of differences in my bubbles. And I bet you all do too. Any other differences that you're seeing? So far, we just have size. That's probably not enough to tell us what is a better bubble, right? Go ahead, keep bubbling away. Man, my skim milk is still to the very over my cup. That's pretty interesting. All right, what are people seeing? And I'm going to write them down because it's really hard for me to remember. Well, so far we only have one characteristic. So that's, one is clear. I have clarity. Very good. So far we have clarity. We have one is darker, one is lighter. Interesting. We have size of bubbles. Okay. So all these things that we're mentioning. All right. Oh, good. And then we have length of time that they're sticking around because the whole milk bubbles don't pop very quickly. Okay. So I'm going to put all this in a lovely data table. All right. Scientists love data table. It's because this is a great way to communicate your findings between different researchers, right? If it's written down, I'm not going to run around all over the place and just verbally say, hey, mine had more. And no, instead we write them down, right? So we have size. So I'm going to write down size. And then we had clarity. Pretty fancy word for if they're clear or they're not so clear, right? And then we had length of time that they stuck around, right? So let's call that duration. That makes sense, right? Duration of the bubbles. All right, what else? Keep going. Let's do it a couple more times. See what we got. All right. Whoa. Okay. What else do we have? Try something for me. All right. We're going to do a test called swipe ability. Okay. I'm going to add that to my characteristics. All right. So swipe ability. So what you're going to do is you're going to get a nice big mound of bubbles. And then you're going to take your straw and you're going to slide it across and you're going to see, are you able to slide your straw all the way across and not lose any bubbles? Or if you do it, do the bubbles just shove off the side? So let's give it a test and let's run this together. Okay. All right, so I'm going to swipe it. Oh, my skim allows my straw to go all the way through it, no problem. Whole milk? Whole milk pretty much the same, but it's a little more difficult to push my bubbles. Okay. Interesting. Okay. We're going to try another one. All right. And anybody know what the state dance of Wisconsin is? No? Has no one ever polka'd at family events or weddings or outside? So state dance of Wisconsin is the polka. So the next test that we're going to try, we're going to call the polkability test. Okay. And I'm making these up. You can make these up as well. All right. You're the scientist. You can make up what you want to test. So I'm going to call this polkability. All right. And how are you going to do that?
Liz, I think Evan's got a question about the polka. He's got lots of question marks there. I don't know. How does the polka dance work?
You need two people to really do it correctly. You know what I mean? But it's like it's not really a very complicated dance. Very good.
So hopefully that helps Evan out a little bit there.
All right. So for our polkability test, you can use your finger. And you'll probably get different results from your finger versus the straw, right? Because there are different characteristics with your finger. Your finger possibly has some grease on it and whatnot on it. All right, and your straw might be a little smoother. So pick. Oh, never heard of it. Never heard of the polka? I don't know if I can handle these guys anymore. All right. So pick your device. All right, and then let's blow some bubbles again, and let's see what happens with polkability. Which bubbles are easier or more difficult to poke? Okay, I'm gonna use my straw. For me, the skim is easier to pop. Maybe I'll try with my finger now, see if there's a difference. Ooh, it's way easier to pop with my finger. Actually, they're both about the same with my finger, but with the straw, I found that it was more difficult to pop the skim bubbles. Okay. So these are a lot of characteristics that we can test, right? But anybody come up with any other tests that they want to try? Anything else you want to try for characteristics? Oh, did we do? Yeah, you could time it. If you haven't timed how long your bubbles stick around, you could do that. If you haven't tried duration yet to see how that works. But I think across the board, generally, we're finding that skim milk sticks around a little bit longer than the whole milk, but you can time that to get a good, a good quantitative or a good number for how much longer it sticks around than the other type of bubbles. Okay. Oh, how heavy is it? Oh my gosh, should we check it out? Because we have a balance right here. Let's check it out, my friends. I love that. So let's look at the mass of them. That's fantastic. Thanks, Evan. All right. I love that we're in a space that we can do that here. All right, so let's see. I'm gonna do it without the straws just to make it fair, right? All right, and let's see what we got. Hopefully it's not so heavy that I can't get it, but let's see. Okay, all right. Let's zero it. All right, I'm gonna try the skim milk first since I have identical cups. That's not a variable that I'm worried about, right? Okay, that's too heavy. I'm gonna try my other scale. All right. This one can sometimes handle, since these are so precise and we're usually working with very small amounts of stuff, it's a little more difficult to get. So let's try it again. This one, crossing my fingers, this won't be too much for this. Ooh, okay. Skim is 112.3 grams. Write that down or you're gonna forget it, right?
Liz, before you take that off, I had another question that Evan helped me really think about. When we use the straw and we blow into the straw, I'm wondering if the mass might change with that too, and if that would be a way for us to do better experiment over time if we think about that, like how much air we're blowing in.
Oh, interesting. To gauge your amount of air that we're blowing in. That's a really good idea. I wonder how we could do that. We'd have to, I mean, I know that there are lung capacity machines, right, that some people use after they've had surgery. So I bet if we can get our hands on one of those, it may help us work on maybe capacity and figuring out what amount we're putting into it. That's a really good question.
Yeah.
That's awesome.
Yeah, and it all, that question came up because Evan had a question, which is kind of a great way that science operates.
It is like somebody will be like, oh, wait a second, that's good, but what about this? So that's why great minds think alike is so very true. All right, because you get a bunch of us in a room and we're like, well, what about this? And what about this? And what about this? Instead of you being by yourself, you get really focused on like one thing, right? But when there's everybody else around you, these great minds around you, they're coming up with really good stuff too. This is why it's great to have all of you here with us helping with this, because mass, honestly, we've never done that before. So now I'm going to bring a balance with me and we're going to do mass whenever I do this again. So that's great. So 112.3, very good. Now let's check out the whole milk. Whoa, I am curious. 97.78. That is surprising to me actually, but I'm writing it down though. 97.78. So our whole milk actually had less mass than our skim. Wonder if I lost some of it. Because another good thing, all right, like everyone was talking about, like I was talking about mass and we're talking about the straws. If you had bubble volcanoes, you maybe lost some of your mass, right? Or there's still possibly some in the straws, right, that we didn't take an account for. Or me like lifting it out and putting it on the table, I have lost milk as well when I have done that. So maybe not super but there's a way to make it more accurate, right? We could measure that even before we started blowing bubbles, and then we would get a more accurate amount. So, I love this.
And you made me think about another thing as we're going through all of these experiments is you can measure a change over time, like how it changes after you do each step. That would be really fun. These scientists are really, really helping to make science happen.
And the thing that we mentioned before, remember, was temperature, because that's also something to think about, because we've been doing this now for, we probably had our milk out for about 20 minutes plus. So when you take it directly out of the fridge, you probably have different qualities or different measurements of your bubbles than now that it's warmer. Because you may be, and I've seen to notice it more with whole milk, that the whole milk goes down even faster as it gets warmer. So that temperature, if you really want to do it right, we really should have this on ice, right? So that we're not having to deal with that temperature situation. So there's ways to deal with that, but this is a little difference that we have to kind of just deal with.
Yeah, and Evan does have a question about that,
Yeah.
about when you put things on ice, he's wondering about how cold milk can be. What is your experience? Have you got it to a temperature where it freezes, and then does this work then, or like, I don't know.
That's a great question. And what kind of we accidentally had to because usually we always get it out of the fridge, right? So we're always generally starting with cold milk and whatever your refrigerator is. But yeah, I've never really taken it to freezing. But I started to, during COVID, I started to ship powdered milk to people. And when we started to do this, it was the only way that you can dissolve powdered milk is to use like room temperature water. Because otherwise you can't, kind of like we were talking about temperature and why stir plates often have heaters as well to bring that into solution. So you have to use room temperature or warmer. And then if you try this with, and maybe leave your milks out, and if you want to try it again in an hour or 2 hours, or wait for your milk to come to room temperature, I couldn't get a single bubble to form when it was room temperature milk. So I started to stress out a little bit, and well, how is this going to work? But I put it in the fridge, and it was in the fridge for about an hour. I took it out. It behaved exactly like the fresh liquid milk that had been in the refrigerator. So temperature really does play a pretty big role in how bubbles are formed in milk. These are excellent questions. So as we've been doing this, has anybody gone back to our original question of which makes better bubbles, skim milk or whole? Because what does better mean? That's a pretty ambiguous question that I gave you there, my friends, because to me, I look at this list of characteristics, and to me, what I think is most important is I think the size of bubbles is pretty important for it being a better bubble, but that probably is different than all of you, right? So how you form your question is incredibly important in science as well. So if you have a very general, ambiguous question like, hey, what's a better bubble? What does that mean to the scientists? All right. And we have a lot of food scientists on this campus, and they are always thinking about these questions, right? Because think about ice cream. All right. Now, to most people, ice cream is best when it is really smooth, right? And doesn't have a whole lot of bubbles or chunks in it, but not necessarily. All right. Because some people may say, you know what? I like a skim milk ice cream, or I like iced milk instead, because I don't want it so dense. All right. I want it to be a little more airy. So food scientists, and thinking about chocolate, right? We all love chocolate. But if you would just say, hey, what's a better chocolate? What does that mean to a food scientist, right? That's studying that. So how you frame questions, incredibly important in science as well, right? And if you look at the containers for the milk, all right, I'll put them up so you can maybe see it. All right, what did you just eat, Travis? All right, so if you look at you see, okay, here's the whole milk, and then here's the skim milk. What's the only major difference between whole and skim milk? What do you think, my fellow scientists? What is the only major difference between whole and skim milk? And if you have your milk containers in front of you, you can look at it as well. Because what are we really testing, right? Well, amount of fat. Okay, anybody else? I like that response because it's true. Because if you look at the amount of fat, all right, there's 8 grams of fat in whole milk, and there is 0 in skim milk, okay? So we're really testing milk fat, right? Because that's really the only major difference between these milks. Oh, protein, interesting. Sometimes milks have, oh, you can maybe even see, does it have protein content? Ah, they're the same. Hey, good question. Oh my gosh, I hadn't even really thought about protein, but protein the same in both, 8 grams of protein. Great question though, because I wasn't sure either. All right, good. And now, ooh, okay, cool. So there's some kind of cool things about milk. All right, you got to talk about this a little bit because I'm on the UW-Madison campus, right? And there's some pretty important things about milk, right? Because vitamin D, very important, and vitamin D is in both of these milks, all right? And vitamin A is in both of these milks. Vitamin A was discovered right here on this campus, and vitamin D wasn't discovered, but Steenbach was, the scientist was able to find a way to use UV to beef up the amount of vitamin D, because vitamin D is really important for children and for adults. So kind of cool stuff happening on campus. And another cool thing, all right, is that maybe you guys have heard of a guy named, everybody gotten ice cream at Babcock before on campus? Really tasty ice cream. Well, Babcock is known for the, oh, question, oh, maybe not. Oh, if you've never gotten ice cream at Babcock on campus, I recommend either come have a field trip, all right, and come on over here. We can run some experiments, and then we can take you to get some ice cream, or just go with your family sometime. So it's named after Babcock because of his really important milk fat test. Because back in the day, sometimes farmers would sneak in a little extra water, or they would change the amount of fat in their milk, and they would be like, I'm going to sell it for the same amount. Well, that's not really fair, right? So Babcock found a way to test the amount of milk fat so that farmers who had more milk fat in their milk would get a better price than those who sometimes adulterated or changed their milk a little bit. All right. So kind of amazing stuff happening on this campus relating to milk and dairy. And we have cows on campus. If you've never seen them, it's pretty cool to go to the dairy barn and see the cows. Some of them have holes in their stomachs, so you can see the grain go down and see what happens. So a lot of neat stuff happening. All right, so I want to make sure that I can get some questions if we have any.
Yeah, so let's open it up to final questions about just some general science questions, things specifically about how to do a great experiment. I think, man, I learned a lot today. And it's always fun to think about how many experiments I've done, and it's always great to learn more. So what about y'all? Evan's got a question about milk freezing, but any other kind of questions that you might have about science and scientist Liz or anything like that. We've got time for maybe 1 or 2 questions more. And then we've got a whole opportunity to just keep experimenting. I'm inspired.
Yeah, this is what I love. So this question about it freezing, this is good because what you can do is if you have those ice cube trays at home, those have these multiple, like 8 little spots, right, or more that you can put samples in. So why not? You can even put them right across from each other. Put in one little area some skim milk, right across from it from whole milk, put in the freezer, come back every 5 minutes and look, or even every couple, however many minutes you decide, and then see which one freezes faster at which temperature. So stick a thermometer in there, so there's a lot of at-home experiments that you can do with things that are edible. Because what's cool is you can eat the data as well, right? Like Travis was drinking the milk. So you can absolutely drink or eat your data. That is fine. Well, I
did. Well, you hinted about chocolate, and I happened to have one M&M sitting there. So I had a chocolate M&M and a little glass of whole milk, but now my data is going to be corrupt.
But it's good questions about like then you can try different milks as well. Like what about strawberry milk? What about chocolate milk? What about 2% milk? What about 1% milk? So we only showed 2, right? But there's a lot of other things that you can do with testing different types of milk as well.
So I have one more question if there is time here. And I'm wondering about the individuals that are scientists that you meet on the UW-Madison campus. Our idea of who's doing the science is really important in terms of how we connect and think about our futures. Can you describe, is there like one type of scientist on campus, or like how would you describe that?
Oh no, there are so many different types of scientists on campus. We can't even name them all, right? There's everything from, and not even, and get into things like mathematicians and data science and computer science. So think about, sometimes we have this idea that it has to be something related to, you have to have a bunch of beakers, it has to be in chemistry, it has to be biology, you have to be looking at Petri plates. That's science. That is not true. There are right up the street, right up the road from where I am, they're working with textiles. So those are scientists working with different types of fibers that you can put together. All of the engineers across the street from where I am, there's so many different types of engineers. They are all scientists as well. So the experiments that they are running are so different and so unique, but there's not really one person or really one way that a scientist looks on this campus for sure. That's a great question, a great way to think about it.
Well, we are so joyful to be able to have this experience, especially around lunchtime too. So I don't know if that's kind of a coincidence. So thank you for all of our youth scientists and adult scientists that joined in today. We really appreciate that. Special shout out to you, Scientist Liz at BioTrek and UW-Madison Extension. Really appreciate that. A recording is going to be available for this field trip. We'll follow up with teachers about that. Remember, the festival, Wisconsin Science Festival, is going on through Sunday. So you can check out events at wisconsinsciencefest.org for more fun science. And we've got things going on all across the state. So wherever you are, you can search by location, and then there's online things more available there as well. So see you there. And thanks, everybody.